Welcome to Mrs. Mahoney's podcast 3.3. This is page 7 in your packet. Today we're going to talk about the average atomic mass. You need to get out your periodic tables and a calculator as well as your packet so that you can be working some of these problems with me. So if you look on the periodic table, what we're going to be looking at today, we know that the top number is the atomic number. That comes from the number of protons. We talked about the mass number, which is just a counting number of neutrons and protons. Today we're going to look at where that actual number comes from on the bottom of the periodic table. This is known as the average atomic mass, and it really, if you notice, it's not a whole number, and so we're going to kind of look at why isn't that a whole number. So the first thing we're going to do is borrow this animation, or use the animation from the University of Colorado, and we're going to just look at some different isotopes. And let's look at the true isotopes. So this is hydrogen's isotopes. Now if we look at this, this is saying that I have a hydrogen 1 proton has 0 neutrons, and I have hydrogen 2 that has 1 neutron and 1 proton. So if I'm looking at it, 99.985885% is actually from that hydrogen 1. There is actually a hydrogen 3, but it's in such a small amount that we really don't even, it gets calculated, but when we start doing the calculations, you're going to see what a small contribution it has. Let's look at some other ones. Helium. Okay, helium again, 99.9999% is the helium-4 with 2 protons, 2 neutrons. But look at over here. I have my one little purple. That means that's a different isotope. That's my helium-3 that only has 1 neutron. Are they all like that? Well, look at lithium. Lithium, you see more of a split. 92.41% is lithium-7. But 7.5% is lithium-6, so that's why you're seeing more purple dots. There's more of another isotope. How about beryllium? Well, nope, 100% is one isotope. Boron. We're seeing almost an 80-20 split there of the two different isotopes. How about carbon? Again, majority is carbon-12, but there's other isotopes there. Nitrogen. Again, not a big split. Oxygen. Now look at here. All of a sudden we're seeing all the purple, which is our oxygen-16, 8 protons, 8 neutrons. But over here we have our oxygen-18, which has 10 neutrons and 8 protons. But look at, we have another different color of our oxygen-17. This one has 3 isotopes. Fluorine, only 1 pretty much. Neon, again, 3 isotopes. Sodium, pretty much the 1. But magnesium, look at my split here. 78.99% magnesium 24, but then a pretty even split of magnesium 26 and magnesium 25. So what happens then, to do our calculations, we need to take into account 2 different things. One, how much do I have of that? And then the second one, what is the mass of that one isotope? Those 2 components are going to make up the average atomic mass. So it's a calculation, and it's an average calculation, but you kind of need to put away all of our traditional averages of how you do that away. So a definition, I would just write down this definition. You will see a definition like this. What is it? It's just a weighted mass, and you have to use all the isotopes of an element. I need to know 2 things. The mass of each individual isotope and the percent abundance, or how much I have of that isotope. So just at the top or somewhere, just write down that definition. Okay, the calculation we say is different, but it's really not a hard calculation. A traditional average, you would, if I had 3 numbers, add them all up and divide by 3. But what you're assuming in a traditional average is that everything is contributing the same amount. We can't do that here. So let's look at a first example. So this is the same example that you have in your packet. So calculate the average atomic mass of an element if I am given the relative abundance of each isotope. This is copper. I have two different numbers. So I have copper 63. Now look at this is the actual mass for copper 63. If I rounded this, I'd round it up to 63. But there's 69.1% copper 63. But I have 30%, a little over 30% is coming from copper 65. So the true mass has to be somewhere between those numbers. So we're going to do the calculation. You need this, but I want it as a decimal. So to find it as a decimal, divide it by 100 or just move it 2 places. So don't forget, we need our number in a decimal. Now the answer then is going to have to be somewhere between these two numbers. So when you do these calculations, I always say you're smarter than your calculator. You have the ability to say, does this number make sense? So what we're going to do is just take these two and figure out, okay, what mass do I get from the copper? So change it to a decimal, times it by that mass. 62.93999590. And it's like, okay, what do I get from this? So 43.54. Now I can either label this U or AMU, atomic mass unit or just unit, same thing. They mean exactly the same thing. Some books, some different places call it the same thing. So if you see an AMU, you see a U. They mean exactly the same thing. So in that isotope, 43.54 of its mass is coming from that copper 63. Well, I have another isotope. This one I have 30%, but I'm going to change it to a decimal, times the 64.927793. So how much is coming from that? 20.02 is coming from that. Well, there's both in there. Final answer, add them together. So I just add that up and you get 63.56 atomic mass units. And again, 4 significant figures here, so I wrote this to 4 significant figures. 4 significant figures, 4 significant figures, adding to the decimal place your 4 significant figures. Look at your number on the periodic table. That's where that number comes from. You have to take into account two things. How much do I have of each isotope and the mass of each one. Let's just do one more, and we can do this all together as one step. And this is also when, let's go back, and I said you've got common sense. So if I look back up here, I said the number needs to be between these two numbers, closer, kind of closer to 63. Well, actually it's going to be between those two numbers, closer to 63. Is that what I got? Yeah, that number is logical to me. I feel comfortable with that answer. Let's look at another one. So if I look at this one, I have 3 isotopes. So what does that mean? I just add all 3 together. So I'm going to just do it. I can also do it as one big problem. I don't have to stop in between. Main thing, percentage needs to be in 100. So be careful when you have this that you fill anything in with a 0. So when I write this out, what do I have? And the order, it doesn't matter if I do mass first or the percentage first, because you're multiplying here. And I have 90% of that isotope 1. Well, I'm just going to add it to what comes from the second isotope. 99394 times it by your second isotope and add it to your last one. 21.9138, and I have 0.0922, squeezing it in there. You're going to just do that all together in the calculator. But again, before I even do it, I'm getting a number in my mind so that I can know, did I make a silly mistake on the calculator? So the majority of it's coming from 20, an isotope of 20. My answer is going to be close to 20, but it will be a little bit higher than 20. That's what I'm expecting on my calculator. So I plug all that in the calculator, and what do I get? 20.18 atomic mass units means the same thing. That is your answer. So is that number what we expected? Yes, it's close to 20, a little bit higher than 20. I'm comfortable with that answer. That number makes sense to me. So what I want you to do is to try the next one. Now there's a little typo on just as far as the formatting. So if you look at that formatting, for some reason magnesium 24 got bolded and highlighted. This is what it should look like. So just work on this. We're going to start tomorrow in class by checking your answer on this. I want you to double check your math. Does it make sense? I also then want you to look at that last question. The element of boron has an atomic mass of 10.81. However, no single atom of boron has a mass of exactly 10.81 atomic mass units. Explain why. If that was facing you on a test, how would you have answered that question? So tomorrow we're going to do some practicing of this in class. So come prepared with questions, or if you have anything you want to ask of where that number came from, we're going to be going over that tomorrow in class.